And what we saw was that a single loop circuit was a nice special case that we knew how to solve. It allowed us to do some things with regard to simplification. We could combine all of the voltage sources together. We could combine all of the resistances or impedances together and make one source, one resistor, solve for the current through the loop, and then we can do whatever else we needed to do. So that's one type of problem that you should look out for in quizzes and exams. You see a single loop, should be a no-brainer. The other type that we saw or we introduced was the single node pair. So the single node pair is, again, another special case. It's one where all of the elements are in parallel with one another, meaning that there's only two distinct nodes in the circuit. There's the top and the bottom, node 1, node 2, and all of these are in parallel with one another. So there's only essentially one voltage in the system. All right? V1, V2, the voltage across all of these guys is going to be equal to Vs. Now you may, in a single node pair circuit, you may not always have a voltage source. So it may not always be known a priori, but it'll just be one voltage. So if we look down here, for single loop circuits, there's a single current that will either be known or we'll have to calculate for, solve for. And then the real problem is going to be getting the individual voltages of the different elements, and we can use KVL for that. And for a single node pair circuit, I shouldn't really say known. I should say there's only one value. There's only one voltage differential across the entire circuit, and so the real problem is going to be parsing out the individual currents. So maybe this is not, I don't know what the right word is here. Shouldn't be known, maybe common. Right? There's a common loop current for all the elements and a common voltage differential for all the elements for the single node pair. Current divider we discussed briefly. So current divider is a circuit that allows us to divide current, as the name would suggest. And we presented the expression for that. All right. Actually, did we go over this last time? Sometimes okay, I apologize. I get a little bit ahead in the other section. Where did we stop in this section last time?
We stopped at multiple sources and resistors.
At this one? We stopped right here. Okay, I got it. All right, so rewind the tape. Let's start over here, and I will give this a more thorough introduction. Okay. So, single node pair circuits. What is a single node pair circuit? It's another special case where for a single node pair we know that the voltage across all the elements is the same and their currents sum together at both of the nodes. We have two nodes. All the currents for all the elements sum to 0 up here. All of the currents for all of the elements sum to 0 down there. We know that the voltage Vs will be equal to the voltage R1, voltage R2, voltage across IL, or across the current source. And so, like I said before, the single loop and the single node pair circuits, I feel like I'm saying the same thing twice. This was a bad way to start class. Why don't I do this? What questions are there on what I just said? Because I went through it really quickly, and then that way I can address the holes in what I said. So what is it? What parts of it are students did you not get from that very quick overview that I gave? Does everybody understand the the basis behind the single node pair? Yes.
Not exactly.
Okay, yes?
So is it basic, just making sure I understand.
Go for it.
So it's basically due to the specific situations that single loop and single node pairs create, you have the fact that current is conserved over resistors, and then you have voltage being conserved over branching points. So because of that, you're using current and voltage respectively for your point?
So I don't know if I would put it that way. Here's the way that I would put it. Problems become easier whenever you reduce the number of variables. A single loop circuit means, in a single loop circuit, there's only one current, which makes the problem easier to solve because we can isolate that and say, first we come up with the current, and then everything else can be taken away from that. In a single node pair, we only have one voltage, which again makes the problem easier because we can focus on solving for that first and then get everything else. It will normally be relatively easy to solve for these values because there'll be so many equations that refer to it. Like for example here, right, the voltage across these terminals is equal to Vs. The voltage across these terminals is equal to I1 times R1. The voltage across these terminals, I2, R2. There'll be like a whole bunch of different equations that all refer to the same value, which means that it'll most likely make the substitution and the combination easier. So that's the idea behind the single loop and the single node pair. It sort of gives you a good starting point and most likely a value that you can just use very easily to calculate everything else. For example, for the single node pair, once you get the voltage, you can calculate all the currents using Ohm's law very easily, right? If we know what the voltage is here, I1 is V divided by R1, I2 is V divided by on and on, et cetera, et cetera. So aside from my rough start to this class and sort of forgetting where we ended last time, this is actually a concept that almost explains itself. Because if you understand how the single loop worked, this is a similar type of
So
thing.
what I said wasn't wrong, though, right? Like that's not.
Well, I mean, the thing about...
Like what, if I have a misunderstanding?
So this class is, it's difficult to get the language down. Like voltage being conserved, current being conserved, you know, it's just, you know, usually we talk about energy being conserved, you know. I could say maybe KCL talks about current being conserved because it, you know, we don't lose any current coming in and out of a node. I think the language was maybe the idea behind it was okay, but the language wasn't exactly describing it the best way. And that's just really, I think, as you progress through this class, it becomes easier to describe things. And that's the reason why we rely so much on the math.
Because that's how it's explained to us, at least in physics too.
So say it again. They say the voltage is
They say
conserved.
voltage is conserved over over junction points?
Yes.
And then current is conserved over resistance. Resistances, right?
Not so much conserved, but like it has the same. So across multiple resistors, you got the same current, and across parallel portions in a circuit, it would have the same voltage.
I agree with that.
Absolutely.
Yes. I think maybe their use of the word conserved in physics was a little bit different from the way that I would use it. Every field has a slightly different, you know, connotation to the words. That description, yes, because that's exactly what we're saying, right? Same voltage across all the terminals, same current through all of the elements. I mean, I guess you could say it's conserved. Anyway, I just usually, when I think of conserved, I think of energy, I think of power, something more so on that side. Okay, so now the current divider. So the current divider is a single node pair circuit, as you can see. And it is the complement, in a certain sense, to the voltage divider. The voltage divider takes in a voltage and allows us to generate a lower voltage, a stepped down voltage. And the ratio between the input and the output is defined by the ratio of those resistors. Same thing here. If we have an input current coming in, and we assume that the current flowing across this resistor is our output, okay, then the output is equal to R1 over R1 plus R2 times whatever the input current is. The reason why I say opposite resistor right here is because for the voltage divider, it's the load resistor that goes in the numerator, right? For the current divider, it's the non-load resistor, right, which is R1, that goes in the numerator. It's an easy way to remember the difference between the two of them. They have the same form. Voltage divider has the load resistor in the numerator, and current divider has the non-load resistor. This circuit, you're not going to use as much as the voltage divider, and really the main reason for that is we don't have as many in practice, in building and using physical circuits. There's not as many real current sources that we come across. Current mirror is one that I think of, and you can build good current sources in certain linear ranges using different combinations of components, but more times than not, voltage sources are what we see. Most signals are going to be transmitted as voltages. Anyway, you get my point. So be aware of this, but it's definitely not going to show up, like for example, when we talk about ENG212, it's not going to show up as much as the voltage divider. Thank you so much. I'm sorry to ask you. I neglected it. Leave it upstairs. Okay, so we're going to do the same thing that we did with the voltage divider, and we are going to try to derive the transfer function for the current divider. All right, so our circuit, we know how it looks, has a current source coming in, and we have two resistors . So I in, R1, R2, and this current right here is our I out. We have a voltage across all of the elements, which I'm going to call V node pair plus minus. That applies to everything. So I'm going to keep including that in the problems for a little while. There's only one current we haven't labeled, and that would be I1 right there. So everything else now is labeled. All right, so we generate the expressions that we know. I know,
Go up a little bit.
yeah. So I know this may seem a little bit repetitive. We're going to start moving, after this chapter is done, we're going to start moving a little bit more quickly, because when we get into nodal analysis, into mesh analysis, we're going to start skipping more steps. We're going to start saying, okay, solve this using algebra. So for those of you who think that the class is maybe creeping along, you'll get what you're looking for soon. But I do like to spend a little bit of time here in the beginning just to make sure that we're fleshing out all the questions people have about the most basic aspects of circuit analysis. Again, applying Ohm's law, applying KCL, applying KVL properly, all those sort of minuscule things. So what expressions do we have? We know that I in is equal to I1 plus I out. All right. We know that V and P is equal to I1 times R1, which is also equal to I out times R2. And I think those are really the only two value expressions that we have. And this one should be pretty easy. So we want to generate an expression that's in terms of IS or in terms of I out, right? Essentially, we're trying to get I out over I in. So let's combine these two expressions together. So we know that IS will be equal to we called it IN, sorry, is equal to V and P over R1, right, that's taken from here, plus V and P over R2. We could combine those together. We have V and P times 1 over R1 plus 1 over R2. All right. One problem with this expression right, we need I out in this expression in order to get the end result, which is I out over I in. And so what we're going to do is a little bit of the opposite of what we just did, and we know that VNP is equal to I out times R2. So we'll push that back in to our expression. And that essentially gives us R2 over R1 plus R2 over R2. We can get our I out over I in. That will be equal to 1 over R2 over R1 plus what is essentially 1. Right? We'll multiply like we did before by R1 over R1 in order to get the fraction out of the denominator. And what we'll end up with is R1 over R1 plus R2. And that's the same as above. So that's nice. That works out. Yep, sorry. I'll leave that up there for a sec. So lastly, before we go to the quiz, I'm going to try to get through this example and solve them. We'll go to the quiz. So now we're going to move on to a different type of problem. We're going to solve a circuit that is neither a single loop nor a single node pair. We're going to learn lots of strategies. I mean, this is really the reoccurring problem in this course. Solve this circuit, give me the voltages and the currents. There's lots of different ways to do it. The first way we're going to learn is to take a circuit that's not a single loop or a single node pair and try to reduce it down to one of those two and see if there's a way that using very small changes we can do that. And a lot of times the answer is yes. All right, so this is called IS. It's equal to 900 microamps, or is that? Yeah. 900 microamps. This is 60 kiloohms. This is 40 kiloohms. This is 80 kiloohms. And this is a value that is referred to in the circuit as V out. All right, so taking a look ahead here, how do you think we could solve this? Yeah. You're on the right track. So which two? Well, right now there's no two elements that are in parallel, right? Because there's no two elements that share the same end nodes. I'm going to get to you. I think he's close. I'm going to give him a second to. So there's no two branches that share the same nodes, end nodes. But are there any two that are in series?
Yes.
Okay. So, well, now I'm just going to call it. Which two are in series? Just somebody.
40K and the 80.
The 40 and the 80, right? The 40 and the 80, these two are in series with one another. We could combine those together. When we combine those together, we'll lose V out. We'll lose that resolution. Yes?
Isn't 60 also series?
So no, the reason why 60 is not in series is because of this. Remember, series means that there's no other path for current to flow from the middle node. So these two are in series. These two are not in series. Anytime there's something else connected there, it breaks that. So, right, we could combine the 40 and the 80 together, which will make a single resistor. Now, will that combo resistor, will that be in series or in parallel with anything else? Actually, you with the teal. That's going to be in parallel with the 60. So then we can combine those two together as parallel, and then we're going to have a circuit that is actually both a single loop and a single node pair, right? The simplest version of that fulfills both of those. And then what you could do is you could solve. You could solve for the voltage across these terminals, these two nodes, and then you have to break it back out and get the rest of the values, because you will lose resolution when you combine it down. Yes?
When you combine 40 and 80, do you lose the phase?
You do. So whenever you do these simplifications, you're going to lose resolution. Okay? So some of these values are going to go away, which means that in order to get the final answer, which is V out, you're going to have to, after you get this voltage here, you're going to have to expand the circuit back out. And we'll talk about ways of doing that. But there's one easy way of doing it. If you imagine right here that we know the voltage between these 2 points, what will the relationship between the voltage here and the voltage here be? Does that look like anything? Talked about it last time. It's a voltage divider, right? We know that V out will be equal to 80 over 40 plus 80 times whatever the voltage is at the input to the voltage divider, which is the voltage right there. It doesn't necessarily have to be a source. We just have to know what the input voltage is. So, I mean, right there, we went through all the steps of how to solve this problem. And so all that's left is to actually go and do it. But since we spent that time, so we were just about to jump into this example here, which was discussing how to solve a circuit where we don't have a single loop or a single node pair right off of the bat, right? We had talked about that already. The situation was, right now, if we are given a single loop, we know how to solve. We essentially solve for the single current flowing through the circuit and then solve for everything else using Ohm's Law. And if it's a single node pair, we solve for the voltage across the terminals, and then we solve for everything else again using Ohm's Law. Okay, this one is neither. I think what we did was we went through and we really quickly talked about how we would do it, but we didn't do it. And the way that we said that we would do it was one strategy that we're going to use in this chapter is going to try to make all circuits look like either a single loop or a single node pair. Try to collapse it down, and that way we can use the methods that we've talked about. So how could we do that to this circuit? The 40 and the 80 kilo ohm resistors, they can combine in series. Then that'll make a 120k ohm resistor, which will be in parallel with this. But actually, you don't even have to do that, because once you combine these two together, you'll have the current source, you'll have the 60 kilo ohm, and then you'll have the 120 kilo ohm. All will be in parallel with each other, and you'll have a single node pair. So then you can go ahead and solve it using the methods that we learned for the single node pair. So I did, however, still write down the steps in solving it. And so, like all of our problems, the first step is going to be to label everything. We want to make sure that we have a good idea of what are the values that we know, what are the values that we don't know. Next thing that we're going to do is we're going to talk about our strategy. And as you can see here, the strategy in these 3 steps is what we just said. We're going to simplify the circuit down, combining resistors and sources together. That's the reason why we spent some time talking about that in last class. We are going to solve for that first voltage or first current, and I use that word loosely. What I mean is that if once we get to a single loop, we can call it kind of like the first current or the fundamental current. And then if it was a single node pair, that would be sort of like the first voltage or whatever you want to use, what word you want to use. And then once we solve that, we have to expand back out to increase resolution and get our values back. So that's one thing we didn't talk about here. Once we solve for the single node pair, which is going to be the source, the 60 kilo ohm resistor, and the 120 kilo ohm resistor, we can't find V out right off the bat, right? V out is lost. That resolution will be gone. So we have to expand back out. In this case, yes?
So, I'm sorry, just trying to understand it better. V out, what value? That's just like what's lost between those 2 points?
It doesn't have any inherent meaning. It's just this problem is asking us to solve for V out. What is V out? That's it. This is, I guess, you could consider to be where the load is going to be placed in the circuit. But in reality, at this point, it's just, the problem is just saying, give me what this voltage is. Okay, so we can use a voltage divider in order to expand that back out, right? Because once we divide the two resistors in two, we will have already found out what Vx is. And so if we imagine this as a voltage source, because it is a known voltage, then the voltage applied to a voltage divider, and we'll end up with 80 over 120 times whatever Vx is. Right? So since we've talked about the process, I think we can go through the math relatively quickly. First thing that I did was I created a single node pair. I actually collapsed both of the resistors together. And so all three of the resistors, the 60, the 40, and the 80, once you do the series and the parallel combination, you end up with a 40 kilo ohm resistor. That's the value of this Rx right here. Then we can go ahead and solve for Vx. So Vx is simply going to be determined by Ohm's Law. We know what the current Rx is. We know what the current Ix is. We know what the resistor Rx is. And so, right, Vx will be equal to I times R. Again, just quickly checking that does satisfy the passive sign convention. Still, don't forget stuff like that. Let's be careful. Right, this current will be flowing from the positive to the negative terminal if we assume that the voltage refers to Rx. And so we have 36 volts. 900 microamps times 40 kilo ohms, 36 volts. And then we can expand it back out using the voltage divider, and that gives us 27 volts. Okay. Now, next. We've talked a little bit about some different combinations of sources. We have shown that in the single node pair, parallel current sources can be combined together. We've shown that in the single loop series, voltage sources can be combined together. So here's all the four different permutations of that. We know already that if we have voltage sources in series, we can sum them together. V equivalent here is equal to V1 plus V2. Right? That we've already seen, yes.
What does that say? What happens when we try to pick combinations of what?
Series combination of voltage sources.
Okay.
It's just a table, right? You can see series is the series and parallel are the columns, and then voltage and current are the rows. I'm going to go in a specific order for a reason. So next, let's look at parallel combinations of current sources. We know that when we have parallel combinations of current sources, when we have parallel combinations of current sources, which is the bottom right-hand corner, I1, I2, the I equivalent is equal to I1 plus I2. Okay, now the reason why I do talk about the other two cases last is because they are ones that don't make sense physically, okay? What happens when you put two voltage sources in parallel with one another? Well, first off, unless they have the exact same value, the circuit is not going to satisfy KVL. It's going to violate KVL, which means you have a problem, right? Because if I were to take this loop right here, and this is 10 volts, and this is 12 volts, then what you'll have is 10 equals 12. Okay, or you'll have 10 minus 12 equals 0. Either way, right? That's not what we want. Well, that doesn't make sense physically. So you can't do that. You can do it if both the sources are the same, but if both of the sources are the same, then it's a redundant thing to do. Now, what happens in reality when you combine two voltage sources in parallel? So in reality, there's always going to be some little resistance between the sources, even the wire, right? The cables, the leads to the sources, and the oscilloscope and the DMM, those have some little small resistance. So if you do connect two voltage sources in parallel with one another that have even very close values, what's going to end up happening is the current between them is going to be equal to this minus this divided by a very, very small resistance. And that's going to lead to a very, very large current, which is going to lead to blowing your fuses in your device. So anyway, don't connect two voltage sources in parallel with one another. That is what it's what we call a low impedance path, and it will, at best, blow your fuses, at worst, cause some other damage. Yeah.
What's that purple thing?
The purple thing is that's the small resistance I'm imagining to be, that whatever wire that connects the two will have. It's just indicating that in a real circuit, in a physical circuit, there is no such thing as a short. There is no short circuit. There is no way, no wire that we can use that will physically have a zero ohm impedance. So this creates a low impedance loop, and I put a bad up here to remind you not to do it. Okay? Combining current sources in series, again, similarly, it doesn't make any sense. It violates KCL, because what you're saying is if you were to apply KCL at this node right here, you're saying I1 must be equal to I2. So again, I guess you could set it up in the circuit as long as the values are the same, but it would be redundant. So you're not going to see any problems, and it doesn't make any sense to use that in a design. So series combinations of voltage sources, you will see those, and parallel combinations of currents, you will see those. But the other combinations, you won't. Any questions on that?
Wasn't done with it yet.
Say it again.
Wasn't done with nothing.
Okay, sure, yeah. No problem. All right. I think we're almost done. One more second. Okay. So let's jump into another example here. For this one, I'd like to ask you how to do it and have you take more of a leading role in this. This takes a little bit of a step back. We've kind of talked about single node pairs a lot. But they give us one last example to try to go through it. So what I'm going to do is go through this relatively quickly. We'll just hopefully be able to really quickly say what the steps are, write down the equations, and get the solution. And I'm going to ask you all to do most of the heavy lifting. So give me a second to draw it. I guess the one thing that is novel about this is it's a little bit bigger than some of the node pairs we've seen so far. That's 12 kilo ohms, that's 2 milliamps, that's 12 kilo ohms, that's 4 milliamps, that's 9 kilo ohms, that's 1 milliamp, and that's 18 kilo ohms. And we'll give these some names. This is IR1, this is IR2, this is IR3, and this is IL. And this will also be called VL plus minus, but it's the same voltage across all of the elements anyway. And we have a node 1 and we have a node 2. There's only 2 nodes in this. So, step number 1, label everything. We've done that. And then for step 2, I'm just going to simply write simplify and solve, or combine and solve. And the value that we're first going to be solving for, because this is a single node pair, is going to be whatever the voltage is across the terminals. So, without going into too much detail, because we have done several of these before, let's collapse this. So can anybody tell me how we're going to collapse this into a very simple circuit? Yeah.
Might be wrong, but can you combine all of the sources in the parallel, and then you can do the same thing for the resistors?
Exactly, right? We learned just now that the current sources will add, right, when they're in parallel. So what I will do is I will give this a value, I'll call it IS, and that's going to be equal to, and I'm just going to give it a little arrow pointing up. The reason why I'm going to say that is just so we're going to assume that the reference direction for IS is pointing upwards. Okay? That's not really an official notation, it's just to remind us right now. So what's going to be the value for that? It's going to be 1 minus 4 plus 2, right? So that is negative 1 milliamps.
Go back up a little bit.
Yeah, 1 second. Okay. So now we combine all the resistors in parallel. The equation that we learned so far looked like this. It was R equivalent equals R1 times R2 over R1 plus R2, right? That's going to be a little bit tedious to use if we have more than 2 to combine. There's another version that we actually haven't discussed yet. Let's say we combine their admittances as opposed to their resistances. The admittance is 1 over, well, conductance. Conductance and admittance are the same for the DC circuits. We can combine their conductances in a much easier manner. Conductances sum when they're in parallel. Resistances sum when they're in series. So what that means is that G equivalent is equal to G1 plus G2 plus G3, ... Doesn't matter how many you have. So if we wanted to write this another way, we could say 1 over R equivalent is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Right, that's the same thing as saying the conductances is 1 over R. And so this form right here it'll be easier for us to use that to combine since we have 4 resistors that we have to worry about. Does that make sense to everybody? I mean, you can do it the other way. What you could do is you could use the R1, R2 over R1 plus R2. First you combine these two, then you get the equivalent value, then you would combine that with this one, and then you would have to do it step by step by step, which is going to take more time, more math. So what we know is that 1 over R equivalent will be equal to 1 over, so we can use all 4 of the resistors, 1 over 18K plus 1 over 9K plus 1 over 12K plus 1 over 12K again, which gives us 1 over 4,000. So the equivalent resistance is 4 kilo ohms of all of those resistors combined together. Okay, actually, scratch that. There's one change. The process is right. I'm going to try to follow the way that I did it last time. So we don't actually need to combine all the resistors into one because we know how to use current dividers. So what we're going to do is we're going to leave this last 12 kilo ohm resistor out of our combination. This one right here. Okay? So this value is not part of the calculation. The 4 kilo ohms is a combination of this resistor, and this resistor, and the RL is left out of it. Okay? That's the reason why I scratched it out. Okay, so let's draw our resultant circuit.
So the 1 over 4,000 is still correct?
The 1 over 4,000 was the value I got from the notes, which was the calculation just accounting for the 3 of them together, not all 4. And the reason why we did it that way is because it'll make it easier to find out what IL is. It allows us to keep some of the resolution. Okay, so the resultant circuit looks like this.
Does it say R4?
Say it again.
Does that say R4 there?
Oh, it was originally called R4. That's what it was, not RL. I erased the number and I couldn't remember what it said. Okay. You know, it was a K. That's what it was. Sorry. That's a 12. Okay. I erased that one little line. I couldn't remember what it said. It said 12K. Okay. So, going back here. So what we end up with is this value right, will come down here. Okay, so that will be our negative 1 milliamp. You could switch the direction of the arrow, but you don't have to, right? Sometimes it's easier just to leave everything the way it is. We said that the direction was going to be pointing up. We said that the value is negative 1, so I'm just going to leave it like that. Pointing up, negative 1. All right, now let's draw our resistors. So this is the R equivalent, okay? And then we have our RL. Our 12 kilo ohm resistor, but this was a current that we called IL. And we know that VL, we have to solve for what VL is. All right. So, as you can see here, and I don't want to get too sidetracked, there's lots of different ways to solve this problem. Originally, I was going to combine all 4 of the resistors together, which would have given us a circuit that looked like this. We would have solved for VL. We would have gone back and calculated everything else. The way that we ended up doing it is we solved only 3 of the resistances together, which left us with a current divider, essentially. And now we can solve for IL easier. It'll be a little bit harder to solve for VL. For these types of problems, and I know I sound like a broken record, going over the homeworks and going over the examples is the only way to get a handle on it, because doing it the other way would have been just as correct as doing it this way. So VL is actually not going to be what we're first going to solve for, given the way that we did it. It's actually going to be IL. And that's just a judgment call. So IL will be equal to, what will it be equal to? It's a current divider, right? We know that for a current divider, it works like this. It'll be 4,000 over 4,000 plus 12,000. It's so messy here. Hold on. Let me write this clearer. Okay. IL is equal to 4,000 over 4,000 plus 12,000 times negative 1 milliamps. Does everybody understand why that is? Right, it's the opposite resistor divided by the sum of the 2 resistors together. And so the value that it gives us is going to be negative 1, can't write today, negative 0.25 milliamps. And then what we can do if we still want VL, we can solve for that using Ohm's Law. We know that VL will be equal to 12 kiloohms times negative 0.25 milliamps, which gives us negative 3 volts. And then you could go back and calculate the other values. You could calculate IR1, you could calculate IR2, IR3 by simply using Ohm's Law. So that's another variation on a single node pair circuit where we didn't collapse it all the way down to one resistor and one current source. We actually made the problem, depending on what the problem asks for, sometimes there's a way to make it a little bit shorter. We collapsed it down just to a current divider. So 2 resistors and 1 current source. All right, now let's jump into something that's going to look a little bit messier. I'm just going to name it that. Some of these examples used to correlate to examples from the book. Like, for example, this one is 220, but there's been so many revisions since I started teaching this course. I'm not sure if it lines up anymore. Yes?
Just to clarify, we're still in chapter 2, right?
We are still in chapter 2, yes. The chapters still line up, knock on wood. The material in the chapter still lines up. It's just the individual examples. The numbers don't line up so much anymore, and then a lot of the numbers, they've changed. I'd rather have a set of notes that's good and mistake-free and uses numbers from 3 versions of the text ago than constantly trying to update for the values and every year coming up with new mathematical mistakes. All right, so the circuit that we're going to be trying to solve is going to look like this. And this is going to take me a minute to draw because it's a pretty, there's a lot of stuff going on, let's put it that way. So that's what the circuit looks like. I'm going to give the other nodes some names just to help us see. D, E, F, and G. And that's nice because now if I want to refer to, the one good thing about giving all the nodes names is we can stop sooner or later labeling everything else, and we can refer to everything by the node. So I could just call this I, E, F, right? I don't have to explicitly give it like a name. And we're going to slowly migrate more to that sort of system where we're not explicitly giving everything a name.
missing a value on the all the way far right?
Oh, no, I'm not purposely. Yeah, it's 1 kilo ohm. Okay, so solve for the equivalent resistance RAB. So this is a little bit of a different form of problem than what we've seen before. We're not being asked, there's no sources. There are no sources in this circuit. Okay? So there's no voltages or currents to solve for. It's dead, right? Everything would be 0. But they ask us to solve for RAB. What is the equivalent resistance? Yes. So let me get rid of this. This doesn't make sense. Yeah.
So is that just the? So there's supposed to be an imaginary line between A and B.
So here's what I would say. You can imagine this situation right here. Okay? That's what we mean when we say there's an equivalent representation. If you were to attach, have you guys used the digital multimeter in ENG212 yet to measure resistances? Right, okay. So if you were to take this circuit with all these resistors and you were to attach the digital multimeter to terminal A and to terminal B, the value that it would read would be RAB, whatever the equivalent parallel series, whatever the equivalent resistance is for all of those. From your point of view, or from any external circuit's point of view, that's what the resistance is. It doesn't care if it's made up of 100 resistors in a weird fashion. It doesn't matter if it's in this configuration right here. It doesn't matter if it's just a single resistor RAB. Okay? So when we talk about finding equivalent resistances, we mean electrically equivalent. Okay? For whatever purposes the circuit uses it for, it's the same thing. And so this problem, what it boils down to is going to be finding the next two resistors that we combine together, that we can combine together, combining them, hopefully not redrawing the circuit completely, and then doing it again. Yeah. Oh man, I had this thing plugged in. Is it not working? Weird. Maybe this one will give you some power. Well, I need it for next class, though, is the only problem. Yeah, I know. Hold.
Computer monitor.
Is there one on the computer monitor? I need to do something. If this thing dies very soon, I'll be in trouble. One second. I have the plug part. Oh man. All right, forget it. One last try.
There's always the outlet behind you.
Yeah, my wire's not going to stretch. But this looks like it's charging. We're good. Okay, so let's combine together the resistors. And what I'm going to try to do is I'm going to try to do as many in one step as possible to reduce the amount of time that this is going to take. So what's the first group that you think that we can hit? Yes?
You do like 1 and 2, combine that to 3, and then make it parallel with 6.
Bingo. That's all we can really do in one chunk, is we can find the equivalent resistance between E and G. Well, it's not really the equivalent resistance. I shouldn't say that. We can combine those three together. So the first thing we're going to do is combine those three values together. So I'm going to give that a name. And so that is going to be, so 2k plus 1k times 6k over 2k plus 1k plus 6k, which together, all of that gives us 2,000 ohms. It's ohms. It's 2 kilo ohms or 2,000 ohms. I was using kilo for the other ones. Okay. So, how can I copy this? Anybody know? Huh?
Maybe try pressing and holding.
No, I think what if you just hold it?
I don't know if I did that. Oh, there we go. All right, perfect. Because what I want is I want a version of the original, and then I want one that I can play around with. So, okay. But that's too close together. Okay. All right, so now let's erase all this. And what we're left with is a resistor that is 2 kilo ohms. What's the next set we can do? Yep.
The same thing, I guess, on the other side? The 4, the 6, and the 9?
So, you can do that, but you're going to lose resolution of point B, which means that whatever equivalent resistance you're going to get, most likely it's going to end up being either equivalent resistance AG or something else along those lines. So you want to make sure that you don't lose the point, which is one of the 2 points, that are the endpoints for the equivalent resistance. I'll go you, then you.
Could you do DEG?
Yeah, DEG. So these three have a similar sort of setup. We'll lose our resolution of point E, but again, point E is not really super important to what it is that we're doing, so that should be okay. So we're going to combine the 6, the 10, the 12. Okay. And so that value we can call RDG. And so RDG is going to be a 6 kilo ohm resistor in parallel with a 12 kilo ohm resistor. So it's going to be 10 plus 2 times 6, so 6, right, over 10K plus 2K plus 6K. And so according to the math that I did last time, that gives us a 4 kilo ohm resistor. All right. So I'm going to say do the rest on your own only because I feel like this is a long problem and we're sort of doing the same thing over and over again. So I hope that you guys will all finish this. But, right, what are we going to end up with after we... I will redraw the circuit one last time. Okay, we redraw the circuit one last time, and so what we end up with now, point E is gone, and we end up with a 4 kilo ohm resistor right here. And so the next three that makes sense to combine would be those three, and then most likely these three, and then you would end up getting to the endpoint that you need. Okay? So the answer that we get is RAB is equal to 5 kilo ohms. Part of this, a big part of this class, it's different than in electronics. It's different than, I don't know, advanced engineering math, right? That's another course that you guys are taking now. That course is honestly hard. There's lots of different stuff that's being thrown at you. A lot of it is not very similar. Method of undetermined coefficients, Laplace transforms, and it's like over here, over here, over here, over here. This course, although a lot of people, it's not considered to be an easy course, there's a lot of repetition. Like, for example, this problem is one of the more difficult problems we've gone over, but if you just know how to apply the same thing over and over again reliably, without making mistakes, knowing where the endpoints are supposed to be, keeping straight, which values are in series combination, which one is a parallel combination. As long as you do that and you have the housekeeping taken care of, then getting the right answer is easier. Okay. There is one type of simplification that we haven't talked about yet that you cannot do using the current tools that you have, the current methods that you have. And so what happens if you see a combo of resistors that looks like this? Okay. So if you have a circuit that has some combination of resistors that looks like this, we can use, there's a transformation to go back and forth that actually makes it easier to solve the circuit. And I think the best way to illustrate this is when we get to an actual example. But for example, just to introduce it, let's say we're trying to find the equivalent resistance to some circuit and it's attached to these, right? How are you going to combine this together? None of them are in series with one another. None of them are inherently in parallel with one another. So given what we know so far, you would be at an impasse. All right? Sometimes what can help is we can convert this form over to this form, and now you may have series and parallel combinations that exist with the external, whatever the rest of the circuit is. So I'll talk about how to go back and forth first, and then second we'll talk about how and when it's going to be useful. The most important thing to realize is that this is like when we do the transformation, it's like we're just cutting along the green line, pulling out whatever's there, taking it and putting it right back in that same spot. Okay, so there's two parts to this. There's understanding how to do the mathematical transformation, which is easy. Okay, it's just a couple equations. And then number two is understanding exactly what it means. After you do the transformation, you cut along the green line, you pull out what's there, and then you put in its place the other version. The terminals A, B, and C need to line up. All right? So how do we do the conversion? Or actually, the next question it asks is, so before we talk about how to do it, let's go through an example. I'm not going to solve it. I'm just going to show a circuit where this would be useful. So we have a voltage source. And we have this configuration. So I'm going to call this point A, I'm going to call this point B, I'm going to call this point C, I'm going to call this point D. And this will be RAB, this will be RCA, this will be RBC, and then I'm just going to give these other two, well, actually I can just call them BD and RCD. Okay. So in this area right here, given the methods that we know so far, we wouldn't have any way to solve this. We don't have any way to make any is there anything that's in parallel? Is there anything that's in series? Nope, nothing. But what if, and I'm not going to show the math of how to do it, just that it could be done. what if we took these three and now we replaced it, and so if I redrew the circuit, again, cutting along the line, pulling it out, and now I gave you something that looked like this. So this is point A, this is point B, this is point C, this is point D. This is going to be a new value. This is going to be a new value. This is going to be a new value. We haven't talked about how to define those yet. This is RBD, and this is RCD. Okay? So your original ABC now has become that. And sorry, I think one thing I didn't say was we say delta to Y transformation. This is called the Y form because it looks like a Y. This is the delta form because it looks like a delta. So you can see that if we take a look at an example here, and I take the delta, yank it out, replace it with a Y, now this becomes very easy to solve. These two are in series with one another, right? These two are in series with one another. Then they'll become in parallel, and then this will be in series with everything else. Right? So the delta to Y transformation, what it does is it allows us to make changes like that we can move on forward with the problem. All right, so now how do we do this specifically? There's two different cases that we have to worry about. So in the case where all of the resistors are the same value, meaning that RA is the same as RB is the same as RC, we can use this form here. So RA equals RB equals RC, and we can just call that simply RY, or the resistance for the Y configuration. And then if they're all equal, we'll have RAB is equal to RBC is equal to RCA, and we'll call that R delta, right? Meaning that up here, right, this would be a value of RY, and this would be a value of R delta, if we were using it in that fashion. And so the transformation, very simple. RY is equal to 1/3 of R delta. Very easy. That's it. Now there is another case. Which is unbalanced. So the resistors are not the same. Note that I said impedances or resistors. All of the rules that we're applying to series and parallel combinations of resistors, delta to Y transformation of resistors, they all work for impedances as well. So later on, when we're talking about AC circuits, they'll also work. The only difference will be that now, or then, you'll have to take into account values that have both real and imaginary parts. So when you do the math, it'll be complex math. But we won't worry about that right now. Okay, so for this one, there is more equations. If we want to get our value RA, that will be equal to RCA, RAB over RAB plus RBC plus RCA. Right, so if we were taking a look at the delta, so if we want to get RA, we would have to multiply this by this over the sum of all three. That's what that's saying. And this value right here, the denominator, I'm going to go ahead and call this RABC for the delta. It's the sum of all of them together. Or maybe a better name is I'll call it R sum delta. Okay, RB is equal to RBC times R, let me put them in order. RAB, RBC over R sum delta. RC is equal to RCA, RBC over R sum delta. One little trick you can see about the numerators is, right, it's just the two resistors that touch the node. Right, for RA it's RAB and it's RCA. For B it's AB and BC. Essentially you exclude the one resistor that doesn't have the letter in it that you're concerned with. Over here, I know we're close to the end. Over here, when we're doing the opposite direction of the conversion, RAB is equal to RA, RB plus RB, RC plus RC times RA over RB. And what I'm going to do is I'm going to call this numerator right here, I'm going to give this the name R sum Y. And so the other two versions, we have RBC will be equal to R sum Y over RC, and RCA will be equal to R sum Y over RA. So that table gives us all the different unbalanced conversions. Obviously on this side you have the Y to delta, and then on this side you have the delta to Y. All right? So we'll go ahead and stop there. For everybody who's going to be signed up to take the makeup quiz, please be prepared to take it next time. Yes? It's going to have all the same requirements. It won't necessarily be similar to the last quiz, but where the stopping point that I set in the book, the stopping point I set in the homework, all of those same things will apply again. And I'm going to find a way to do it pretty quickly because I don't want to take up a lot of time. So I don't know. I gotta mull that over a little bit. All right. We'll also next time start talking about our next real quiz, our quiz number 2, which will most likely be at the end of next week. But we'll talk more about that when the time comes. Homework-wise, also, I want to set a date for the completion of the Chapter 2 homework, which I will be collecting this time. So, tentatively, I'm going to say this. And we can discuss more when next class.